Today we're going to be writing equations of exponentials, and in order to do that I want to go ahead and review some of the stuff that we've done to make sure you understand the basic exponential. So we talked about the basic exponential growth and the basic exponential decay. They're both in the format y equals b to the x value. B being greater than 1 is a growth. So we have a sketch. That looks like this. When b is between 0 and 1, so the number that's being raised to the x power is between 0 and 1, we get a decay. And the graph of that looks like this. For our domain, that part is easy with exponentials. It's all real numbers. You can write that as all real numbers with the r with the two lines, or you can write it as negative infinity to infinity. Either one of those would be correct. It's all real numbers because it goes all the way to the left and all the way to the right. So we have every x value represented on this graph. For our range, we only have the positive y values. It never touches the x-axis and it doesn't touch anything below it. So we have no negative values and no 0. So we start with 0, we go up to infinity. This is the asymptote and up. And it is a parenthesis since 0 is not represented on that graph. So you do not want a bracket here, you want a parenthesis. The x-axis is the asymptote. It guides your graph forever this way. It is a horizontal line, and all horizontal lines are y equals. So this has a horizontal asymptote at y equals 0. Since it's not touching the x-axis, there's no x-intercept. So this only has a y-intercept, and it is at 0, 1 for both graphs, the growth and the decay. That's because anything to the 0 power is 1. So they're all going to have this point right here of 0, 1. That's an important point on the graph of an exponential. For our end behavior, on a growth, it is starting really close to the x-axis here, and then it shoots up pretty quickly. So as x approaches negative infinity, which is the left-hand side, y is approaching 0. It's approaching that asymptote. And as x approaches positive infinity, y is approaching positive infinity because it's going up forever. On this case, as x approaches negative infinity on the left-hand side here, it's the opposite. It's going up forever. So y would be approaching positive infinity. And as x approaches positive infinity on the right, y is approaching 0 because it's getting closer and closer to this asymptote here. For increasing and decreasing, our growth graph is always increasing. It starts at the bottom and then starts to go up. So it is always increasing. So our domain would be all real numbers. It is never decreasing. So we just write none for that one. For our decay, it is always decreasing. It starts at the top, and as we move to the right, it is going smaller and smaller. So this is never increasing and always decreasing. Those are the basic attributes of these exponentials. So I wanted to make sure that you had them reviewed before we start to write our equations. Now we're going to start writing our equations. In order to do that though, what is an exponential? We want to talk about that. Here we have some real life data that we've put into a table of values. Way back when you started to write equations and think about functions, you started with a linear one. And so we'll go back and review some of the stuff that you know just so that we can get through this part. With a linear one, you looked at the differences in your y's here, the first differences. And so that's what we're going to start with here. When we look at our first differences, we've got 4, 6, 10, 15, 22, 25, and 31. Those are not constant. Our first differences here are not the same, so that tells us it is not linear. After you looked at the linear equation, you went and looked at the quadratic equation. You found the second differences was what told you if it was quadratic. So you took the second differences here. And so we have a difference of 2, a difference of 4, 5, 7, 3, and 6. These are also not the same. Our second differences are different. Now we know it's not quadratic. All right, so how do we know if it's exponential? Well, we know that by something called the successive quotients. We check to see, instead of the differences, if the division, which is quotients, when we divide these, if it gives us a constant number. So we're going to take that 14 and divide it by 10, and that is 1.4. Then we take the 20 and divide it by 14, and that is 1.42. We take the 30 and divide it by 20, and that is 1.5. We take the 45 and divide it by 30, and that is 1.5. And then we take the 67 and divide it by 45, and it is 1.48. So looking at these numbers, they're all off by 0.1 is the biggest difference on all of these right here. So these numbers are considered constant for real life data because they're very similar to each other. They're right there next to each other. So these successive quotients were constant. That's what tells us it's an exponential function. Once we figure out it's an exponential function, now it's time to write the equation. You can write it the easy way, the way we did it the other day on the calculator. So you can go to your TI-84, or you can go to your Desmos, or whatever calculator you're using to do your equation. Remember, that was stat edit, stat calc, and that was exponential regression. The calculator does the work for you there, and it gives us this equation of y equals 9.91 times 1.45 to the x power. So let's look at this equation. This 1.45 is the average of all of these right here. That's what your calculator is doing when it writes the equation for you. It finds these successive quotients and it finds the average, and that is your growth factor. So these successive quotients are your growth factor, the B value that it gave us right here. We talked about this other one right here. This is the A value. That's our initial amount. And so if you go back to our table, we see that at 0, it is 10, which is 9.91 rounded. So this part right here is our initial amount, and this is our growth factor, and our growth factor comes from these successive quotients. So now we're going to write this algebraically instead of with the calculator. So here we go. Here are some tables for us to practice that. We find our successive quotients. So we're going to divide 48 by 12. We're going to take 192 and divide it by 48. And we're going to take 768 and divide it by 192. There is our constant successive quotient. It is 4. So that right there is our growth factor, which is the B value. To find the A value, we need the initial amount. In this particular table, 0 is not there, but we can find 0 easily. We can see that each time they multiplied times 4 here. So in order to get this value here, we would divide by 4, and that gave us 3. So this right here is our initial amount. That's the one that happens at 0. And so our equation is y equals 3, which is my initial amount, times 4 to the x power. There it is algebraically. From a graph, it works similar to the form that we do a table of values. Now, in some cases, that's not going to work. So here, that's going to go, it's going towards 0. So we've got a horizontal asymptote at 0. So this is going to work the same way because it's just that y equals a times b to the x. Now, in this case, we see that there's a horizontal asymptote, so we do need to think about our transformations. Remember, the calculator cannot write this equation because it doesn't do transformations, and since our horizontal asymptote has moved, we know there's transformations there. So we'll do these two right here. I spot at 0, 2. There's my first point. That's going to give me that initial amount. And so my initial amount there is 2. So far I have that equation right there. I know the initial amount, I don't know the growth factor. So I need another point to find that growth factor. So right here, they've given us another point that is -1, 6. And so now I can write that equation by plugging in the 6 for my y and the -1 for my x. I divide by 2. 3 is equal to b to the -1 power. Remember, anything to the negative power, we do the reciprocal, so we want to flip that. So that's going to be 3 is equal to 1 over b. We cross multiply and get 3b is equal to 1, and then we divide by 3, so b is equal to 1/3. Now that we have our growth factor, or our decay factor in this case, we have y equals 2 times 1/3 to the x power. We wrote the equation. All right, for this one here, we see that our horizontal asymptote is at y equals 1. So we know this graph has moved up 1 unit. Now the point that's supposed to be at 0, 1 is at 0, 2. It also has moved up 1 unit. That tells us that our initial amount is still that 1. So we've got the equation y equals b to the x plus 1. That's the movement up 1. Now we can do our successive quotients because we've got several different points here, or we can plug in a point like we did on this last one. Since they've given us all these points here, I've got plenty of points to plug in. So I'm going to plug in the 3 in for y and the -1 for the x. I subtract this one to get it to the other side, and I get 2 is equal to b to the -1. So 2 is equal to 1 over b. We cross multiply, and then we divide by 2. So b is equal to 1/2. I knew it was going to be between 0 and 1 because this is a decay here. So I knew our factor had to be between 0 and 1, which it did. It's 1/2. And so our equation is equal to 1/2 x plus 1. So there's writing the equations algebraically using those successive quotients. All right, now we're going to expand that exponential function that we've been dealing with. So we have been talking about this one right here, the y equals a times b to the x power or t power as it has here. This is the initial amount. And b is our growth or decay factor. We're going to expand that b value to talk further about what is going on with that growth and decay factor. So we've got two different ones here, one for exponential growth and one for exponential decay. So that b value has been expanded to be this 1 plus r or 1 minus r. And it's written down here, 1 plus r is the growth factor and 1 minus r is the decay factor. Once that's simplified, it turns into that b. But what is this in here? Well, 1 stands for 100%. You know, when we change percent to a number, we move that decimal over 2 places. So that's 1. So this is 100% of what we started with plus whatever the rate is that it's growing at. And so the rate tells us it's a percent change. And you want to write it as a decimal. And this would be 100% minus whatever percentage it is decreasing by. So that's where this equation comes from. This equation is used very, very often. So we're going to go ahead and show you some examples of how that happens in real world. This first one, it says in 1995, there was 285 cell phone subscribers in the small town of Brushville. The number of subscribers increased by 75% per year until 2005. What were the number of cell phone subscribers in Brushville in 2004? Don't consider a fractional part of a person. You want to remember that people, you're going to want to round to the nearest person. All right, so what is the initial number of subscribers? That was 285. So that is going to be the value I place in A. What is the rate that the number of subscribers is growing at? Well, that's 75%. That's the R, that's the rate. And we want to change that to a number. So we're going to move that decimal over 2 places to get 0.75. Write the equation for the situation and find the answer. So in this case, to write the equation, we need to think about what the growth factor is. It is increasing, so this would be 1 plus 0.75. That would be our growth factor. 100% of the people we started with plus 75% is what's increasing each time. So that gives us 1.75. So our equation would be 285 is the A and 1.75 is the B. Now, in order to figure out how many people in 2004, we would take this 1995 up to 2004, that was 9 years. So we're going to plug in 9 for our time. And so we get y is equal to 285 times 1.75 to the 9th power. We plug that into our calculator and we get 43,871.99. Now, we said we don't want to leave people in our answer as 0.99. There's not fractional people, so you want to either round or truncate. We take both of those answers. So you want to do something like 43,872 subscribers. All right, we're going to look at another real-world example here. A black Mustang costs $40,000 new and depreciates at a rate of 12%. Find the value of the Mustang after 5 years. How long will it take for the value of the Mustang to be less than $18,000? What is the initial amount of the Mustang and what variables does this represent? So our initial amount would be $40,000. So A is going to be equal to $40,000. All right, for what is the rate that the Mustang is depreciating at? Depreciate means it is going down in value. So this is going to be a decay equation. And it's going down at 12%. So our rate is 12%, which we said we moved the decimal over 2 places, so that's going to be 0.12. For the decay factor, we have the 100% minus the 12% that it's going down each year, which gives us 0.88. That right there is a decay factor because it's between 0 and 1. So we know this is going to be a decay graph. That's how it turns out. So when it's plus, it's going to be above 1 and give you something like this. When it's minus, it turns out to be a number between 0 and 1. So we get that growth factor and the decay factor. Write the equation for the situation. And so our equation here would be y equals 40,000 times 0.88 to the t power. All right, this other one's asking us, when is the Mustang going to be less than 18,000? In order to do that, we need to solve these. And we're really not going to get to solving until the next unit, but you can do this in the calculator, so I want to show you that. All right, so I've taken one side of the equation and placed it on the y1 and the other side of the equation and placed it in y2. We've done this before to find when that is equal to each other, since we don't know how to solve exponentials just yet. So we can do it with the graph. So I've opened up my window to make sure that I can see the entire graph. So I'll go ahead and show you the window real quick. I opened up the x values up to 50, and then I opened up our y values to 50,000 so that we can see that entire value of the car. Now that point where they intersect is where they would be the same price. And so I hit second, trace, intersect, enter, enter, enter. And there's that intersection at approximately 6.24 years. Your other option is to use the table of values. And so we can go to our table here and we see that it is too far there. When we start at 0, there we go. When we start at 0, you see that it is 40,000 right there, and then that's our price each year after. So we want to get to where it's 18,000, and so we see right here is the closest, right at 16. It's getting to 18,000, so sometime after 6 years, it's going to be 18,000. All right, so I'll go ahead and write that there, y2, y1, and find the intersection. If you do that with Desmos, same thing, you would plug 1 into y1, 1 into y2, and find that intersection between the two. And so we found that it was 6.2. 6.25 years for the Mustang to be approximately 18,000. Oh, sorry, that one says 17,500. 18,000 was up in the problem. Sorry about that. All right, for our last one here, it says, suppose you start with $100 and it doubles over the course of the next 3 months. How much money do you have after those 3 months? So write the equation that models the money doubling every 3 months. All right, so with it doubling, if you think about what happens when you double something, you start with 2, for example, and when it doubles, you would say it has 4. In order to get this equation, it would be the 100% plus 100%. That's what's going to give you that doubling. So I'm going to write some of those here because they are used quite often so that you can think through them on the growth or decay factors. When they say double, that means we're multiplying times 2, the 100% plus 100%, which gives me the 2. When it says triples, that's going to be 3. When it says it halves, that's 1/2. We'll get to half-life, which is the same thing. It halves, so we're multiplying times 1/2 each time. Now this one's a hard one because you do have to think through all of that. It tells us here all right. So write the equation that models the money doubling every 3 months. So we're going to write our equation. We started with $100, so that's our A value. We just said it doubles, so that's my B value too. Now, if I just put a T here, it would double every single measurement of time, which in this case is months. And we don't want it to double every month. It says every 3 months. So we need to divide this time by 3. That way it's not doubling every month, it's doubling every 3rd month. Because that's the same thing as 1/3 times T. So the first month it'll do a 1/3, the second month it'll do the second 1/3, and then on the 3rd month it hits the double. So that T needs to be divided by 3. That part is very important. These are the harder types of problems. You got to think a little bit further on what's going on here. So divide by 3 because it is not every month. All right. How much money would you have after 2 years? Here's another thing that they do that's tricky. They change the measurement of time. It is not in months anymore. This equation is written in months, so you have to use the same measurement of time. So we need to convert this. And so we get y equals 100 times 2 to the 24 divided by 3. We plug that into our calculator and we get 25,600. That's how much money we'll have after the 2 years. With money, remember you want to leave 2 decimals if there's any decimals. All right, how long would it take you to have 204,800? We're going to do that exactly like the one we did above. Because now we're looking for the y value. So we would plug one side into y1, the other into y2, or use the table, and we find that t is approximately 33 years. And suppose that it triples, what would be the equation that models that? So remember, what was doubling was this part here. So if we tripled it, then we would change that portion of the equation. We still had 100, which is the initial amount, and it was still happening every 3 months, so we still have this t over 3. What would change is that growth factor. Instead of doubling, it would triple. So there's some real life situations that have these exponential growth and decay, and now we can write those equations.